So we're going to go ahead and do this analysis here for two circuits, looking at the current for some missing resistors here. And we keep in mind that with current, the thing we're really thinking about is junctions, okay? We know that the current going into the junction must be equal to the current leaving the junction. That's our key idea with current. And so what I'm going to do is I'm just going to start and say the current's going in one particular direction. So we'll say it's going kind of around our circuit in a clockwise direction. It doesn't actually matter what you pick. Either way will work, but we'll just pick this way for it doesn't matter. So this is the first junction really. The current's going to go along here, go through the resistor, and it's going to get to this junction here. And it's going to split. And we know that some current goes this way, some current goes that way. The amount of current that goes down at that junction is 1.3 amps. Right? And we know that because that's how much current flows through this resistor. The amount of current that goes straight is going to be 1.5 amps, because we know that's how much current goes through this resistor. So that means that A, right, which went into that junction, must be equal to 1.3 plus 1.5. Current going in must equal current going out, so that means that A has 2.8 amps of current. That 1.5 then continues along here and comes to this junction. We see here that 0.7 amps goes through the path to the left. That means that the remaining 0.8 amps, and again, these two need to add up, 0.7, 0.8 need to add up to that 1.5. So the remaining 0.8 amps goes to the right, which means C has 0.8 amps of current. Those two come together, the 0.7 and 0.8, to create 1.5 amps of current flowing through that bottom portion. That 1.5 combines with the 1.3 amps flowing down to create the current that ultimately flows through B. So the current through B must be the sum of this 1.3 and this 1.5, which means we have 2.8 amps going through B. And that makes sense because then that 2.8 amps is going to continue around through the battery and back to A, where we still have 2.8 amps. So let's go ahead and look at our second current circuit here. And so once again, I'm going to say that the current's going around this circuit in the clockwise direction. It comes to this first junction here, and we know that there are 4.3 amps of current going into that junction. We see that's how much flows through this resistor, and that's going to split. Some is going to go down, some is going to go straight. And we know that the current going in must equal the current going out. So if 2.1 amps goes straight like that, the remaining current, which is going to be 2.2 amps, must go down. So going through D is going to be 2.2 amps, and that works because then this 2.2 that went down and this 2.2 that went straight add up to the 4.3 that ultimately went into the junction. Let's continue and do F here. That 2.1 amps goes through that resistor. There's no junctions then before getting to F. So that means that we're still going to have that 2.1 flowing around through this entire branch. And so F will also have 2.1 amps. The current has nowhere to go. When you have one resistor right after another, they must have the same current because there's no junction for the current to split off. But this one, we do have a junction. Okay, that 2.2 comes in this junction. We see that 0.9 amps goes that way. The remainder, which would be 1.3 amps, must go to the left. So that means 1.3 amps will go through E, because that 1.3 then and the 0.9 add up to the 2.2. Those two currents then come back together, all right? And so we have this 1.3, the 0.9, and the 2.1 all coming together to ultimately give us 4.3 amps. When they all come together at this junction, going back to the battery and then continuing on through the circuit. All right, for this next one, what we're thinking about here is voltage. And with voltage, our important rule is that each loop must add up to the voltage of the battery. So we're going to be thinking about our loops, our possible pathways through each of these circuits, knowing that the voltage across the resistors in that loop must add up to the total voltage of the battery, which is 25 volts here. Alright, so to start this one, I'm going to think about all the possible loops that I could take going through the circuit. So one possible loop is this blue pathway, just taking the inner loop here. The next possible loop is going to be this green pathway, where I pick the left resistor on that far end. And then my final loop that I could take would be this red pathway, basically the same as the green, but I go through the other resistor. So thinking about each one of those, I'm going to use that to figure out the voltages for our missing things. So let me start with the inner blue loop here. And so what I can do is, I know everything must add up to 25. So I have resistor A, which I don't know, and then 11 and 16. So what I really need is, or 11 and 6, so I really need 6 plus 11 plus A to equal 25, which means that A here is going to be 8 volts. All right, so that adds up to 25. My next move I'm going to do here is I'm going to think about this green loop here, which goes through B, and then this 5 volt, or that resistor with 5 volts on it. And so thinking about that green loop there, I have resistor A, which is 8, plus resistor B, which I don't know, plus 5 plus 6. Okay, and so that's going to allow me to find that resistor B, since it all needs to add up to 25 here. Okay, resistor B must be 6 volts. That will allow it to add up to 25. And then lastly, I'm going to think about the far red loop. So I have this loop all the way out here. And so for that one, I have 8 volts on the first resistor, plus 6 plus resistor C plus 6 must equal to 25, and so I find that resistor C must also be equal to 25, or equal to 5. So two things to point out here. Notice that these two resistors, which we would say are in parallel, have the same voltage. That is a little trick you can use. Also notice that this pathway is 11, this pathway has a total of 11, and this pathway is also a total of 11, and that's going to happen anytime the circuit splits and then comes back together. Every path must have the same voltage across it. Alright, same thing as I did before. I'm going to think about all the pathways through the second circuit here. So one pathway would be this red pathway here, going through that innermost loop. I could also take this green pathway and go through E instead of going through D, or I could take the pathway that goes all the way around the outside, that blue pathway there. All right, so I'm going to start with the inner green pathway, or the inner red pathway, keeping in mind that all this has to add up to 40. So thinking about that inner pathway, what I end up getting is I have that 10 volts plus 12 volts plus resistor D must add up to 40. And so I solve for D, and I find that D is going to be 18 volts. So that's that one there. I do know immediately now that E is also 18 volts, but I can set that one up again as well. Thinking about this pathway, we have the 10, the 12, and then E. So if we add those up, 10 plus 12 plus E must also equal 40. So we would find that E as well as 18 volts, but they're in parallel, so I knew that ahead of time. And then lastly, the blue outer pathway, we have the 10, we have the 22, and then resistor F. That needs to add up to 40 here, so 10 and 22 and F must equal 40, which means that F is going to be 8 volts. Alright, so for this circuit here, we're basically doing what we've been doing for the past two problems, filling in missing voltages and currents using our voltage rules and our current rules, which, as a quick reminder, are that for voltage, every loop must add up to the voltage of the battery, and for current, the current going into a junction must equal the current leaving the junction. So I'm going to start out with voltage here first. The other thing I'm going to keep in mind with voltage is that resistors in parallel must have the same voltage. So when it splits like this and the current can either go one way or the other, those two resistors in parallel must have the same voltage across them. So I'm going to first just label all those parallel resistors and make sure they're the same voltage as the one that's in parallel with them. So we see here that resistor E must have a voltage of 10 volts because it is in parallel with resistor C. And we see that this resistor F here is in parallel with this other resistor which gets 12 volts, so F must also have 12 volts. From there, I'm going to think about my loops, and keep in mind that each loop must add up to the voltage of the battery, which is 100 in this case. So starting with this inner loop here, that inner blue loop, I'm going to think about that and think about the fact that 30 plus 40 plus A must equal 100. That means A is going to be 30 volts as well. So I can fill that one in there. Continuing on, I'm going to take a loop going all the way around the outside here to ultimately get resistor B. And so thinking about that big outer loop, I have 30 plus B plus 12 plus 13 plus 30, which I know is a lot of numbers here. But if I go and add those up, I end up getting B plus 85 equals 100, which means that B must be 15 volts here. So I can go ahead and fill that one in as well. And then my final loop that I can make is one that goes through resistor D here. That's the only missing voltage now. And so thinking about that red loop going through resistor D, I can say 30 plus 15 plus 10 plus D plus 30 must equal 100. And so that means when I add some of those terms up there, I end up getting D plus 85 equals 100. So D must also equal 15 volts. And so I can fill that one in there. Alright, for the second part, we're going to think about our current rules, and I'm actually going to start over on this far right side here because I know the currents through both of these resistors. I'm going to be thinking about current flowing clockwise around the circuit, although you can do it the other way for sure. So the first thing I'm going to look at is this junction and think about this 3 amps and this 2 amps coming together at that junction, and so that's going to form a current of 5 amps. Which means we'll have 5 amps going through resistor G there. The next thing I'm going to think about is this junction right here. And for that junction, I'm thinking about the fact that the current from E, which is 1 amp, is going to come together with the current from C to form 3 amps going through D, which means that there must be 2 amps going through C, so that that 2 amps and the 1 amp can combine to make 3 amps. I'm then going to think about this junction right here, okay, where I have 3 amps coming through D and 5 amps coming from this branch. That's going to come together to form a current of 8 amps, which then will in turn combine this junction here, that 8 amps and the 2 amps coming down from this resistor above will combine to go through resistor H. They'll combine to make 10 amps. And so that means H gets 10 amps. That 10 will go up through the battery and continue along to A. Since there were no junctions in between, that means resistor A also gets 10 amps. That eventually comes here to this final junction right here. Okay, and we see that that 10 amps that's going in is going to split. We know 2 amps goes down, and the remainder goes straight, so resistor B here must have that remaining 8 amps that goes straight. And so there are all of my currents along with all of my voltages. So for this next one, we're going to be ranking the current going through this series of light bulbs. It is important here that all of these light bulbs are identical. That will matter when we're going through the problem. And again, we're thinking about our current rule that current splits at junction. So I'm just going to think about how this current flows through the circuit. So current's going to leave the battery. All of it goes through light bulb 1. It then comes to this junction. Some is going to split and go through light bulb 2. Other current is going to take this green path around through light bulb 3. That all is going to come back together at this junction here and all go through light bulb 4. So in terms of a ranking, both light bulb 1 and light bulb 4 get the full current no matter what path the electrons take through the circuit, they must go through both of those light bulbs, which means 1 and 4 must be equal. Okay, then we think about the current splitting to 2 and 3. They're going to get less because they don't get the full current, but they're going to get the same amount, and that's where that the light bulbs are identical comes in. Okay, when the current splits at this junction, it's not always going to split evenly in all situations, but because we know that light bulb 2 and light bulb 3 are the same, it will split evenly here. Okay, and so for our explanation, we would just say that both 1 and 4 get the full current of the battery. However, that current splits to light bulb 2 and light bulb 3, so each of those will get half the current because they're both identical. All right, and then for this last one, it's similar to the previous problem, but now we're ranking the voltages. Once again, all of the light bulbs are identical, but for voltage, we're thinking about loops around the circuit. So I'm going to think about all the possible pathways I have around this circuit. So one possible pathway is this blue loop when we only go through light bulb 1. A second possible pathway is this green middle loop when we go through light bulbs 2 and 3. And my final possible pathway would be this red loop which goes all the way around the outside going through light bulbs 4, 5, and 6. And so, keeping that in mind, we know that 1 is the only light bulb on its loop, so that gets the full voltage of the battery. That's got to be the greatest amount of voltage. Then we see that 2 and 3 are going to share that voltage, so 2 and 3 together must add up to the voltage of the battery. Each one will get half, and again, this is a situation where they happen to split the voltage evenly because they're identical bulbs. That won't always happen, but it does in this case. So 2 and 3 are equal to each other. And then if we think about 4, 5, and 6, they're also sharing the voltage of the battery, but then it's split 3 ways, so they're going to be the least, but they'll all be equal to each other. Explanation-wise, we can just say kind of what we just talked about. 1 gets the full voltage of the battery because it's the only bulb on its loop. 2 and 3 split it in half because they're on their own loop. And then 4, 5, and 6 split that voltage into thirds because they're on yet a separate loop.